last homework assignment?
No, there will be one more homework assignment, but it's mostly concept questions, and it's just on the last topic of internal combustion engines, and it's really easy assignment. So this is our next homework assignment. Again, we're still talking about entropy, so this is the last assignment from Chapter 7. The notes went out. I don't know where. There's extras somewhere. So this homework assignment will be due a week from today, and then I think it's like 2 weeks from today, 3 weeks from today is our final. So we have pretty much 2 weeks left of class. I'm sure that's good news to get through this stuff. Okay, so we're continuing on with our discussion of entropy. And similar to developing an equation for boundary work for closed systems, we want to come up with some similar way to analyze open steady flow systems. So that's what we're going to kind of talk about at the beginning of lecture today. And if you recall, any work that's done during the process depends on the path that we follow. So I've used the analogy before. I can get from this corner of the room to the opposite corner of the room in many different ways. Some of them may require more work than others. So today we'll lead into a discussion of how to minimize the amount of work that needs to be done in order to accomplish a specific process. So as we develop these equations, it's important to remember again that they have very specific conditions under which they apply. So as we say something is applicable for an ideal gas or applicable under isothermal situations, I want you to make sure that you keep that in mind so that the conditions under which you can apply it in your homework problems are specific. So if you remember, for a closed system, when we talked about boundary work, we had this area under the curve is equal to PdV, and we were able to graphically or mathematically determine the boundary work done just based on physical properties, so pressure and specific volume. And it would be beneficial if we can come up with a similar equation for open steady flow system. So if you recall that for a steady flow device, this is in differential form the energy balance equation. So del Q reversible in minus del work reversible out is equal to dH plus the change in kinetic energies plus the change in potential energy, and that's in differential form. We also derived previously that this differential term is equal to TdS, or the temperature times the differential change in entropy. And then from the Gibbs equation, we found that it was equal to the change in enthalpy minus V dT. So we're just simply going to take this out of the equation and replace it with this equation. Okay, so now we can rearrange, and we have our negative del work reversible is equal to VdP plus our change in kinetic for our change in potential energy that we could take. So if we integrate that, we find that the reversible work is just equal to this integral, the negative VdP minus the change in kinetic minus the change in potential energy. This first term here is what we're really interested in, because this is an analogous method by which to determine the steady flow work done, again, based only on the properties of the system. So in this case, pressure and specific volume. So our reversible work for a steady flow device is equal to the integral of negative VdP from state 1 to state 2. Okay, so this is just equation magic manipulation that we use to come down with the bottom line for the reversible work. We can make some assumptions to simplify this equation even further. If we assume that it's incompressible flow, what does that mean? What is incompressible flow? Okay, the specific volume doesn't change, or the density doesn't change. So if we assume that, then the specific volume can come outside the integral, and we simply have the reversible work is equal to negative V times P2 minus P1. And again, you have the kinetic energy and the potential energy as well. This one? Nope. And if we have a device that doesn't involve any work at all. So a pipe is a steady flow engineering device that doesn't involve any external work input or has any work output. Then we would set this side of the equation equal to 0. And does anybody recognize this equation, or does it look familiar to anybody?
That's the same equation we use for steady flow.
No, it's different.
Instead it has P.
Yeah, you've used this, hopefully, if you've had fluids, you've used this. This is the Bernoulli equation. So for steady incompressible flow, this is the equation that relates pressure to velocity and elevation changes.
Wait, and that little b, that's specific volume?
Specific volume. So you may have seen it as P2 minus P1 over density, or with specific weight in there somehow. Okay, so this is the Bernoulli equation. We also use it in thermodynamics. And it's always wonderful when you find out that all these different fields are interrelated and that the same basic principles apply in fluids as it does in thermodynamics. Okay, so now we've developed this equation for steady flow, reversible work. And if you look at this equation, it's pretty obvious that it's proportional to the specific volume. So it's V times the change in pressure. If we want to minimize the amount of work we have to put into the system, we can do a couple of things. One, we can minimize the pressure difference that's required, meaning that if we realize we don't have to compress it as much as maybe we thought initially, that would be one way to minimize work input. But minimizing the specific volume is another way. And there's several different ways to do that. One is choosing a different working fluid. Another might be cooling, and we'll talk about that a little bit later. If we have a work output process, we want to maximize our specific volume instead. So if you think about a steam power plant, and I'll just draw the brief picture up here on the board. So we have a pump that goes up to a boiler, which runs steam through a turbine, which generates some sort of a work output, goes down to a condenser, and then back through the pump again. Okay, so when we're pumping a liquid. So that means we have a minimal work input, because if this is proportional to V times P2 minus P1, if we minimize our specific volume by pumping a liquid rather than trying to pump something in the steam form or in a gaseous form, then we minimize the amount of work we have to do here. Similarly, with the turbine, V times P2 minus P1, we're maximizing our specific volume because we have evaporated the liquid after it comes out of the pump. It's at a much less dense state in the gaseous or the vapor form, and as it runs through the turbine, there's more energy available to it that we can harness and receive a work output. Okay, so when we want to minimize the work we need to do, we want to minimize our specific volume. And if we want to maximize the amount of work we get out, we'd like to maximize the specific volume. So let's just do an example. We're going to look at the difference between pumping between two pressures in the liquid state versus in the gaseous or the vapor state. So pumps pump liquids and compressors compress vapors or gases. So we're going to look at the two different conditions. In both cases, we're going between the same two pressure points. So we're going from 100 kilopascals to 1 megapascal. But in the first case, we're doing it as a liquid. In the second case, we're doing it as a vapor. Okay, so what do you think is the first step that we need to do in this process? We're given the initial pressure and the final pressure, and then we're told in part A that we're a saturated liquid, and part B we're a saturated vapor. So what do we need to do? Find the specific volume, and how do we do that? In the tables. Okay, so for part A, at 100 kilopascals, X equals 0, we look up our specific volume, and V1 is equal to V sub F at 100 kilopascals is 0.001043 meters cubed per kilogram. How do we find V2? Or what can we do in order to...
Use the S's.
Okay, we can use the S's. If we use E's, we can do that and we find a V2. Another thing we can do is, because it's a liquid and we're pumping a liquid, we can assume that it's incompressible. So if we assume it's incompressible, that means the density doesn't change. It also means that the specific volume doesn't change. So if we make the incompressible assumption, then V2 is equal to V1. And if we're making that incompressible assumption, then the work reversible in is equal to V times P2 minus P1. Now, I left off the negative sign because I'm explicitly saying that this is the reversible work into the system. Okay, so I don't need a negative sign. The negative sign, if it's reversible work out, then I would put the negative sign. Okay, so the specific volume, 0.001043 meters cubed per kilogram, times P2, which is 1,000 kilopascals, minus 100 kilopascals, which is P1. So we find that the amount of work we have to put into the system is 0.9387 kilojoules per kilogram. So that's the work per unit mass required when we're pumping in a liquid state.
So we don't have to account for kinetic energy.
We're not told anything about velocities in this problem, so, I mean, if we were given that information, we may need to consider it, but generally with a pump, the velocities are so low and they don't change very much that it's not something we have to worry about. Sometimes with the compressor, the fluid will be set up, but usually not significantly. So again, in the absence of any information about velocity, we can't make any assumptions other than assume it's negligible. And in most cases, even when we were given the velocities, it didn't add a very significant difference anyway. Okay, so for part B, now we're looking at the property values. Instead of at the liquid state, we'll look at the saturated vapor state. So V1 is equal to V sub G at 100 kilopascals, which is 1.6941 meters cubed per kilogram. And we're going to need to look up a couple of other property values. H is equal to H sub G, which is 2675.0 kilojoules per kilogram. And S is S sub G, which is 7.3589 kilojoules per kilogram Kelvin. Now we need to find the property values at the second state, 1,000 kilopascals. What is our second independent property value that allows us to fix the state? Entropy. Okay, we're told in the problem that it's compressed isentropically. So S2 is equal to S1. Okay, so now at 1,000 kilopascals, with our entropies equal, we're superheated vapor, and we look up H is equal to 3194.48 kilojoules per kilogram. That was by interpolation. Okay, so in this case, we say our reversible work in is equal to the integral from 1 to 2 of VdP. And in this case, we cannot make the incompressible assumption, so our specific volume is changing throughout this process. Okay, how do we know what VDP is? Okay, well, we could do the energy balance in another way, starting with Q in minus Q out, etc. Or we can prove that all things are equivalent. So if we remember the Gibbs equation, TDS is equal to DH minus VDP. In our case, DS is 0. So DH is equal to VDP. So we can replace the VDP in this equation with DH, which is just equal to H2 minus H1. Okay, if we had done the energy balance from the beginning for a compressor, we would come up with the exact same thing, because there's no work output, there's just a work input is equal to H2 minus H1. Okay, so we just look at the property values that we found in our tables. So H2 minus H1 is 3194.48 minus 2675.0 kilojoules per kilogram, or 519.5 kilojoules per kilogram. So how much work input was required to exact the same pressure difference for a liquid? 0.9. Okay, 0.9 compared to 5 something. Okay, it's more than 500 times greater, causing the same pressure change at the vapor state than it is at the liquid state. Okay, so that's a good illustration of why we want to minimize our specific volume for work input and maximize it for work output. The difference is significant, can be significant. Okay, so just to prove that reversible work is better than non-reversible work or actual work, if we look at the two equations, so this is just the energy balance. The top one is in the actual case, and the bottom one is in the reversible case. So two almost identical equations. One is reversible, one is actual. We can rearrange, because they're both equal to the same thing, dH plus dKE plus dPE, we can set one equal to the other. So the actual equal to the reversible case. And we can rearrange so that work is on one side of the equation and heat transfer is on the other side of the equation. Then we remember that this del Q reversible can be replaced by TDS. Then if we combine terms, so this whole term divided by T and this ds minus del Q over T, so I just divide through by T. And I know that ds has to be greater than or equal to the actual heat transfer divided by the temperature. And this was the, does you remember which inequality that is? The Clausius inequality. Okay, so since this ds term has to be greater than or equal to this term on this side of the equation, then this work reversible has to be greater than or equal to the actual work. Okay, so in every case, your reversible work output is going to be greater than your actual work output. The exception would be in the case where your actual work is a reversible work and then they're equal. Okay, so reversible work is always going to be a greater work output. Okay, so let's talk now. We did a pretty nice example that showed how great the difference can be in the amount of work that's required. So let's talk about the ways that we can minimize compressor work. The first is to minimize irreversibility. So obviously we need to look at the isentropic case and we need to figure out how we can make this compressor more reversible. So if we need to eliminate friction, or if we need to perform the compression process so it's not oscillating, try to minimize vibrations, whatever we need to do to make sure that we have eliminated as many irreversibilities as we can. The second way is to keep the specific volume small. So one way to do that would be to remove heat from the gas during the compression process, or as we talk about later, you can do multi-stage compression processes and remove heat after each stage, or you can be mindful in your selection of working fluid. So there may be a fluid that's better geared towards the pressure drops that you need to achieve that would have a smaller specific volume change under those circumstances. So water may not be the ideal solution that you would want to implement in your plant. You may need to go with a refrigerant or some other type of working fluid. So you can analyze those on a case-to-case basis. So let's just talk about 3 different conditions to minimize the compressor work. And if we look at this equation, this integral of VdP, and we assume that P is in the form of P V to the, we'll say X, is equal to some constant. Okay, we've seen that before. And we plug that into the integral. Depending on what the constant is, we come up with different equations in the end. Okay, if PV to the K is equal to constant, where K is the C sub P over C sub V, it's calculated in the back of your textbook. Then we come up, when we integrate, we come up with this equation for an ideal gas, Kr times T2 minus T1 over K minus 1, okay, which is also equal to this if we substitute pressure into temperature and rearrange. Okay, so depending on whether or not you know the temperature difference at the initial and final state or the pressure difference at the initial and final state, one might be better than the other two. If n is some value between 1 and k, then we can just substitute in n. And this looks identical to the equation above. The difference is that we now have this n value, which is somewhere in between 1 and k, to calculate that equation. And then the isothermal case, where we have maximum cooling, is RT natural log of P2 over P1. And that's in the case where this X, or this superscript here, is equal to 1. Okay, so what does this mean? The isentropic case is the one where we have minimized all the irreversibilities. So there's no irreversibilities in the system. But we're not applying any cooling. Because if you remember, there's 2 different ways to minimize the compressor work. The first is minimizing irreversibilities. That is the isentropic case. The second is keeping the specific volume small. And we've decided the way to do that is through cooling. Okay. So it's interesting to note that for a compressor, the isentropic case is not necessarily the best case scenario. It's the best case as far as irreversibilities are concerned. But we can do additional energy removal during the process by removing some of the heat in order to minimize the work that has to be done on the compression process. Okay, this may or may not add to your cost as you're performing this compression process, but that's one of the trade-offs you have to determine, if it's easier to remove heat or easier to just extend the energy compressing, whatever it is you need to compress. Okay, so this will make sense a little bit better when we look at the graph on the next page. So in the isentropic case, we don't apply any cooling. In the polytropic case, we apply some cooling. And in the isothermal case, we apply whatever amount of cooling we need to so that the specific volume doesn't change. So the constant temperature, constant specific volume process. And if you look on the PV diagram, prior to now, when we've been looking at the PV diagram, its boundary work is equal to P dV, then we said that the area under the curve was the amount of work that either was done or needed to be done during the process. So the work output or the work input with the area under the curve. In this case, because our work is equal to V dP, work of the compressor, it's the area to the left of the curve that represents the amount of work that needs to be done during the process. Okay, so you see the 3 different cases. The isentropic case, where n is equal to k, which is C sub p over C sub v, is this line here. So you can see that the area to the left of the curve is greater than the polytropic case and the isothermal case. So the isothermal case for an ideal gas actually represents the best case scenario for minimizing compressor work. The isotropic case is still the best case scenario for minimizing compressor work if all you're doing is minimizing irreversibility. You're not adding any additional cooling to the system. Okay, so isentropic case is still best case scenario for minimizing irreversibilities or making it a reversible system. But we're going one step further by having some active cooling methods on our compressor in order to improve our performance even more. Okay, so I don't want you to think that isentropic now is like a bad thing. This is like going above and beyond by actively intervening in the system to do something else. Okay. In the absence of cooling, isentropic is still the best case scenario. Okay. So are there any questions on this? Is it all just line over your head? Way up there. Okay, well let's confuse it even more.
So if I'm just running like a basic compressor with just air cooling around it.
Yeah.
Then,
Then you're somewhere over here.
alright,
You're above the isentropic case.
yes.
Yeah. But you could be running a basic cooling system, and even though there's irreversibilities in it or associated with it, basic compressor system, if you're trying to cool that compressor or adding active cooling somehow, you can improve the performance even if you haven't gotten rid of all the irreversibilities. So cooling and keeping that specific volume small is another way to improve the performance of the compressor so that you have to put less work into it overall. But again, there are those trade-offs. So if it requires you to run a refrigerator in order to cool the compressor and you're actually using more work to cool it than you are saving by cooling it, then of course it's not worth it. But you know, if it's the simple difference of having a fan blowing nearby or something like that, then it would make it. Okay. But it's not always practical to cool a compressor as it's compressing a gas. It's somewhat difficult actually in large-scale plants because the compressors are usually quite large and there's so many other bits of machinery around and trying to get in there and add a cooling system like some sort of a water jacket around it may be cost prohibitive. So what we can do instead is cool the gas between two stages of compression. So if we compress the gas halfway, cool it, and then compress it again, that can allow us to have some of the same benefits of cooling without having to try to develop some cooling system for a compressor. So cooling the gas in between by blowing through a heat exchanger or some other method is sometimes easier to implement and can provide almost as much benefit. So in this case, we analyze it in two stages. So we still use this same equation, nRT over n minus 1. But in this case, we're going from P1 to some intermediate pressure, so we're compressing part way. And then we're continuing from that intermediate pressure to our final desired pressure. Okay, so what is P sub x? Well, it can be any pressure that's convenient for you in your process. But if you want the best case scenario to minimize the work, you can find that P sub x is equal to the square root of P1 times P2. Or in other words, when this ratio, P sub x over P1, is equal to this ratio, P sub 2 over P sub x. Okay, so if you want to find the intermediate pressure that will be best suited to your process for minimizing the compression work, then you would just take the square root of P1 times P2. So let's just look at that on a diagram. So if this is the regular polytropic process where we have some cooling, and then this is the isothermal process where we keep the temperature of the gas constant throughout the process, you can see that providing intercooling, so at first we're following along the line for the polytropic process. So the first half of the process going to the intermediate pressure. Then we cool the gas down to the temperature that it would be if we had been performing an isothermal process. So we cool it back down to the initial temperature that it was before it entered into the compressor in the first place. And then perform from that intermediate pressure a compression process to our desired final pressure. So you can see that we save this amount of work here. So instead of continuing along the polytropic line, we bump it over and we're able to save this amount of work. Again, this amount of work saved has to be greater than the amount of work required to perform the cooling process in order to make it worth it. And you can look at it on a TS diagram here, that we're decreasing the entropy by cooling. So we go a slight decrease in entropy because we're compressing the gas and it's changing the pressure, which decreases the entropy, but then as we cool it, it also decreases the entropy further. So it's not a constant entropy process for an isentropic process, which would just be a straight line up. So we're kind of zigzagging along. And we're trying to hover around this intermediate initial temperature. An isothermal process would go straight over. Okay, so let's do some examples of this because it's a little bit confusing to just talk about it in general terms. But this problem is very similar to your homework. And I wrote this note up here to myself to remember to give you a homework hint after this problem. Because there's a tricky part on your homework, and it's simply due to the fact that it's in English units instead of the SI units. Okay, so get out a big piece of paper. It's going to take up a lot of room for this. 7 pages. Okay, air is compressed by a reversible compressor from an inlet state of 100 kilopascal. Okay, so when it tells us initially that it's a reversible compressor, what do we know?
What was the question we were all getting?
If it's a reversible compressor,
Yeah.
then the what does that tell us?
Being reversible, or you want to assume that it's, since we don't have any reversibilities, the ideal case.
Okay, so this is a reversible compressor, and if we don't add any active cooling, meaning we don't remove any heat from it, it's going to be reversible and adiabatic, which is isentropic. Okay, so the basic case that we're starting with is the isentropic case, where we don't remove any heat from it. So determine the compressor work per unit mass for A, isentropic compression, so that's just this basic case. We're not removing any heat with K is equal to 1.4, so that's the ratio of the C sub T, C sub B. Polytropic compression with N is equal to 1.3, and then isothermal compression. Then ideal two-stage compression with intercooling for the polytropic exponent of 1.3. Okay, so this is very similar to the homework problem you have. So this should be pretty helpful to you. Okay, so in the first case, we just simply use the work of the compressor is equal to KRT1 over K minus 1 times the ratio of P2 over P1 to the K minus 1 over K minus 1 quantity. This pen doesn't work good. So if we plug in the numbers for that, K is equal to 1.4, R is 0.2870 kilopascals times meters cubed per kilogram Kelvin or kilojoules per kilogram Kelvin. T is given to us as what? I'm not doing on there. D1 is 300 Kelvin. It's on the picture. Okay, so 300 Kelvin. It's important to use absolute temperature units. K minus 1 is 0.4 multiplied by that ratio of P2 over P1. So 900 kilopascals over 100 kilopascals to the 0.4 over 1.4 minus 1. Okay, so this answer is 263.21 kilojoules per kilogram. I wrote that kind of big, I should have left a little. Okay, so the second case, very similar, part B, but in this case, our exponent is now 1.3, so n is equal to 1.3, but our equation is nRT1 over n minus 1 times the quantity P2 over P1 to the n minus 1 over n minus 1. So if we plug in the same numbers for that, this time n is equal to 1.3, then we get 246.39 kilojoules per kilogram. N is 1.3. Okay, so everything else is the same. For part C, the isothermal case, the equation changes. So n now is equal to 1. So when we perform the integration to develop these equations, we now get RT natural log of P2 over P1. So that's 0.2870 kilojoules per kilogram Kelvin times 300 Kelvin. Natural log of P2 is 900 divided by 100 kilopascals. And that's equal to 189.18 kilojoules per kilogram. Okay, so from the first three cases, we can see how we're reducing the amount of work we have to put into the system. So starting off at 263, down to 246, now down to 189. Okay, so for part D now, we're going to have two compression stages with intercooling. So we need to determine our intermediate pressure. So P sub x is equal to the square root of P1 times P2. So this is the intermediate pressure that will minimize our compressor work.
P1 top, P2.
What? Square root of P1, P2?
Yeah.
I might have said something different. Okay. So this, if we put in the numbers, is square root of 900 times 100 equals 300 kilopascals. So this is the intermediate pressure at which, to which we will compress. So now our equation is similar to this one, but now we have two, well, I'll write it out. So we have nRT1 over n minus 1 times px over p1 to the n minus 1 over n minus 1 plus nRT1 over n minus 1 to the p2 over p times p2 over px to the n minus 1 over n minus 1. Okay, so we have this plus this. But what we did when we found out our best case scenario is we used the fact that px over p1 is equal to p2 over px. So if this quantity is equal to this quantity, then we can combine these two equations together. Is equal to 2 times nRT1 over n minus 1. And then we can either say px over p1 or p2 over px is the same. Px over p1 to n minus 1 over n minus 1. Okay, so by virtue of the fact that this holds true for the best case in determining the pressure at which our intercooling happens,
So
then we can combine those two stages together.
if you said px over p1 is equal to p2 over px in which cases? types of pressure.
So this is the case where we have two different compression stages. So we're compressing to some intermediate pressure, we're cooling back down to T1, and then compressing it again. So if we were to analyze that, it'd be two separate stages. And we want to do the one that has the best case scenario for us, which is when Px over P1 is equal to P2
So
over
we're doing best case now.
So this is the best case scenario for this multi-stage cooling. So it just reduces down to this, so 2 times all of this, and plugging in the numbers, remembering that P sub x is equal to 300 kilopascals. Then we find 215.32 kilojoules per kilogram. So it's somewhere in between these two. It's not quite as good as the isothermal case, but it's better than the polytropic case without intercooling. Okay.
Is that 300 kilopascals the exit or outlet pressure from the first compressor and the inlet pressure from the second?
Yes. Yes. So the intermediate pressure between the two stages. Okay, so now I said I was going to give you a homework hint to make your life easier. On problem 115E, you have helium as an ideal gas and it's being compressed, blah, blah, blah. In order to find the mass flow rate in this problem, because before we were just finding the work per unit mass, but in 115E you have to find W dot. So to find your mass flow rate, V is equal to RT over P, and M dot is equal to V dot over V. Okay, so that's the first thing you have to do to find mass flow rate. The second tip is when you look up R, it's equal to 0.4961 BTUs per pound mass times Rankine. Now, when we work in the SI units, a kilojoule per kilogram is equal to a kilopascal times a meter cubed. But in these units, 1 BTU is equal to 5.404 PSIA times V cubed. Sorry, this is not kilojoules per kilogram, it's kilojoule. Kilojoule is equal to kilopascal times meter cubed. Okay, so 1 BTU is equal to 5.404 PSIA times V cubed. So when you find R in terms of BTU per pound mass, you may need to convert it to PSIA times V cubed per pound mass times Rankine when you use this equation. And in that case, it's 2.6805 PSIA times V cubed per pound mass Rankine. Okay. You will use this value in this equation. But you will use this value when you get down to your equation for W dot. Okay, because the units don't work out otherwise. So be careful to keep track of your units. And when you find W dot, it'll be in terms of BTUs. So you can leave it in terms of BTUs. I have the answers both ways for the grader, or you can convert to horsepower. And the conversion factor for that's in the back of the book. Actually, it'll be in terms of BTUs per second. Okay, does that make sense? So just be very careful in keeping track of your units because it gets wonky with the English system. Okay, any questions on these compressor problems? sort of seems like it's coming out of the blue, like why are we talking about this, right? Okay. It leads to a discussion of isentropic efficiency. So when we were dealing with heat pumps and refrigerators and heat engines in chapter 6, we compared them to what in order to determine the efficiency? The Carnot cycle. Okay, we're going to do some similar comparisons in this chapter. So now we're going to compare to the isentropic case in order to determine an isentropic efficiency. So before we determined a thermal efficiency for heat engines, now we're determining an isentropic efficiency for compressors, pumps, and turbines in this chapter. Okay, so it provides the idealized model, which provides sort of the upper limit for us. So reversible adiabatic cases are isentropic. The important thing to remember is that even though a compressor has an isentropic efficiency that's based on the reversible adiabatic case, a compressor can do better by adding cooling to the process. But that's something that we have to do. It's like an outside process that we add to our system. Okay. But the isentropic case, again, identifies the limits for a theoretical work. So if we look at the HS diagram, and if you remember from before, earlier in the chapter, we talked about how this enthalpy term sort of gives an indication of the energy output of the system, and the S gives an idea of how irreversible the system is. So again, looking at the HS diagram, if we have a line that goes straight down, then we know we have the best case scenario for minimizing our irreversibilities and maximizing our work. Okay, so we look at the HS diagram in order to kind of identify how our process is doing compared to the isentropic case. So if we look, these are lines of constant pressure on the HS diagram. So we have pressure 1 to pressure 2. So if this is a turbine, we're going from a high pressure, we're taking some of the energy out of that fluid, reducing the pressure and the temperature of it, and we end up on this, this line for the exit pressure. So if we do this in a way that is reversible, then we have the isentropic case. However, because we have irreversibilities associated with our system, we actually end up in a slightly different location when we perform the process for real. Okay, so in the isentropic case, we have the amount of work equal to the distance of this line, whereas in the actual case, we have an amount of work equal to the distance vertically between the initial and the final point. Okay, so this is a way to analyze our system and compare it to a known isentropic case and see how close we are. So the isentropic efficiency is defined as the actual work out of our turbine divided by the work that we would be able to achieve if the process were isentropic. Okay. So if we were to neglect any changes in kinetic and potential energy, and we were just to perform the energy balance and determine our actual turbine work, and again, we're also ignoring any heat transfer out of the turbine, then we would find that the actual turbine work is just the difference between the enthalpy at state 1 and enthalpy at state 2, and the isentropic work is the difference between the enthalpy at state 1 and the enthalpy at state 2 if we assume the entropy is constant. So in one case, we're finding the second enthalpy based on the actual outlet conditions. In the second case, we're finding the enthalpy, what it would be if the entropy were constant. So given the outlet pressure, if we assume that the entropy was constant, what would be the outlet enthalpy? Does that make sense? We'll do some examples of these that will help make it make a little more sense. So the bottom line is we're trying to find some benchmark against which to measure our real system. And by doing so and plotting it, especially on this HS diagram, we can see where, how close we are, how far we need to go, what minimizing certain irreversibilities can do to help us get closer to that state. Okay, so let's do an example. We have steam at 3 megapascals and 400 Celsius. So it's a superheated vapor here at state 1. And we want to expand it to 30 kilopascals. So this will be our final pressure in both the actual case and the isentropic case. It's an adiabatic turbine with an isentropic efficiency of 92%. Determine the power produced by this turbine in kilowatts when the mass flow rate is 2 kilograms per second. So we're given the initial conditions, we're given the final pressure, we're given the efficiency of the isentropic efficiency, and also the mass flow rate. So let's just look at how we analyze this system. Okay, let's start out with an energy balance. So Q dot in minus Q dot out plus work dot in minus work dot out is equal to the mass flow rate times H2 minus H1. Okay, we're told that this is an adiabatic turbine, so we don't have any heat transfer, and we don't have any work input to the turbine. So we have work dot out is equal to m dot times H1 minus H2. Okay, this is the equation we would use regardless of the actual case or the isentropic case. Okay, the energy balance still holds true. Now, if we want to find the actual workout or the isentropic workout, we need to add some subscripts on our subscripts here to make sure that we don't get confused. So the workout isentropic is equal to m dot times H1 minus H2S. And the workout actual is equal to m dot times H1 minus H2 actual. Okay, so let's go to our property table now and look up some of these properties. So at 3 megapascals and 400 degrees Celsius, we have a superheated vapor. And we're going to look up the enthalpy and the entropy. So this is table A6. We find our enthalpy is 3231.7 kilojoules per kilogram. And our entropy is 6.9235 kilojoules per kilogram Kelvin. Okay, so this is our actual condition. We start at the same place regardless of the actual or the isentropic. So now let's look at what it would be if the system were isentropic. So H2 isentropic is going to be equal to some value, and S2 is going to be equal to S1. So we know our final pressure is 30 kilopascals, right? And S2 is equal to 6.9235 kilojoules per kilogram Kelvin. Okay, if we go to the tables, we look at 30 kilopascals and S2 at this value, we find that we're actually under the dome. So we have to determine the quality. So S is going to be S minus S sub F over SFG, where S is equal to 6.9235, minus S sub F is 0.9441, divided by 6.8234. So we find our quality is equal to 0.8763. So now we can calculate our isentropic case for the enthalpy is equal to H sub F plus X HFG H sub F is 289.27 plus 0.8763 times 2335.3. So we find H2S is equal to 2335.7. Wait a minute. Oh, that's right. Okay. That's HFG, not HG. Okay. So we calculate our enthalpy for the isentropic case. So we know this, we know this. We're given the mass flow rate in the problem. We can calculate this. So our workout, actually it'll be a W dot because we have a mass flow rate. F is equal to m dot, which is 2 kilograms per second, multiplied by the difference in the enthalpies. So 3231.7 minus 2335.7 kilojoules per kilogram. So that value, I didn't calculate it explicitly because I jumped a step.
$17.92.
17. Okay, so 1792 kilowatts is our isentropic workout. We want to find our actual workout. We know that our isentropic efficiency for a turbine is W dot actual over W dot isentropic. So W dot actual is equal to the efficiency times the isentropic work. That's equal to 0.92 times 1792 kilowatts, which is 1649 kilowatts. Okay, so this is the actual workout of our turbine given the isentropic efficiency of 0.92. Okay, now if we wanted to, if we needed to determine the actual temperature out of our turbine, how do you think we could go about doing that?
Solve for H2.
Solve for H2A. Okay, so we now know this, we know m dot, and we know H1. We can solve for H2A and use that to find the actual temperature. Okay. Any questions on this? All right. So similarly, we can find the isentropic efficiency of the compressor, and this is assuming an adiabatic compressor. So our actual, or our isentropic compression work divided by our actual compression work will give us our efficiency, because the isentropic case will be less work than the actual case. Again, if we can neglect kinetic and potential energy and assuming it's adiabatic, then we determine that the isentropic efficiency is also equal to H2S minus H1 over H2A minus H1. So that's slightly different from before, just flip-flopped from the turbine and the signs are changed. However, we know that for a compressor, there's actually a case that's better than isentropic. We add some cooling to it. So we can compare it to the isentropic case, or we can compare it to the isothermal case. So if we're not adding any external cooling, if we're just comparing to the isentropic case for the compressor, you're giving me a fun look there.
That's the only fun he has.
You're just smirking because it's all. Okay. Okay, so there's two different scenarios in which we might compare. One would be, okay, we're not going to provide any active cooling to this compressor. We're going to compare it to the isentropic case and see how irreversible it is. The other idea might be, okay, we want to look at the isothermal case. We want to add some active cooling. We're going to compare our actual turbine to this isothermal case to see how close we are to that one. Because even though we've minimized as many irreversibilities as we can, we're going to try to minimize the specific volume by cooling it. Okay, so in this case, this is supposed to be a WT, that's isothermal. I don't know why I put a T there. So that's the isothermal compressor work divided by the actual work. So it's just important to remember that the isentropic case is not actually the best case scenario. You can provide cooling and do better. Okay, and then we also have isentropic efficiency for a pump. And again, we minimized the specific volume already by pumping in a liquid form rather than a vapor form. So we don't need to provide any active cooling on a pump. We just look at the isentropic case. And if we assume that it's incompressible, then we know the work of an isentropic pump is just equal to the specific volume times the change in pressure. So let's do another example with a compressor this time. So we have this time air is compressed by an adiabatic compressor from 100 kilopascals and 20 Celsius to 700 kilopascals at a steady rate of 2 kilograms per second. Determine the power required to compress the air if the isentropic compression efficiency is 95%. Okay, so in this case, we have air. We're not providing any active cooling. We're just comparing to the isentropic case. So what are some of the assumptions we can make in this problem? Or can we make any assumptions? I'm assuming we can assume. Are there any? Okay, isentropic. When we determine the isentropic work, what else?
Ideal gas.
Ideal gas. Okay, that's what I was waiting for. Okay, so air is an ideal gas. That will be important to us later. So if we perform the energy balance Q in minus Q dot out plus work dot in minus work dot out is equal to m dot times H2 minus H1, ignoring kinetic and potential energy. Okay, we're told that the air compressor is adiabatic, so there's no heat transfer, and we don't have any work output from a compressor. So we just have this W dot in is equal to m dot times H2 minus H1. Okay, similar to what we did for the turbine, we have W dot in isentropic is equal to m dot times H2S minus H1, and W dot in actual is equal to m dot times H2 actual minus H1. So because this is an ideal gas, and we're assuming in the first case that it's isentropic, we can also make the additional assumption that the specific heat is constant, and that will allow us to say C sub P times T2S minus P1 for C sub P times T2 actual minus T1. In order to find the isentropic T2, we know T2S over T1 is equal to P2 over P1 to the K minus 1 over K. So for an isentropic ideal gas with constant specific heats, we can make this assumption. Okay, this only works for isentropic ideal gas with constant specific heats. To make that clear. So we solve for our T2 isentropic is equal to 293 Kelvin times 700 kilopascals divided by 100 kilopascals, P2 over P1, to the 0.4, well, air 0.395, I guess, 1.395. nitrogen is 1.4, but air is 1.3. Okay, so we have 508.3 Kelvin is our T2 isentropic. So now we can calculate our isentropic work. C sub P, we just assume is at 350 Kelvin-ish, doesn't change very much. So M dot is given to us in the problem as 2 kilograms per second. C sub P is 1.013 kilojoules per kilogram. T2S is 508.3 Kelvin, and T1 is 293 Kelvin. So we find that our isentropic work is equal to 436.3 kilowatts. Then again, our isentropic efficiency for a compressor is equal to the isentropic work over the actual work. So the actual work is equal to W dot S divided by the isentropic efficiency for the compressor. So 436.3 kilowatts divided by 0.95 gives us 459.3 kilowatts. So it actually requires more energy or more power to compress in this actual case than it did in the isentropic case. There. Okay, so this may kind of seem out of the ordinary to insert this piece of the lecture here. This lecture in the series of lectures on entropy. But what we're using now is we're discovering how to use entropy as a tool to analyze real systems. Because it's all well and good to calculate how much entropy is generated in the process. But the real use to us comes in analyzing systems. Okay, we can do similar analysis with nozzles. This time we don't have any work input or output. We just have kinetic energy. So the isentropic efficiency of the nozzle is due to the velocity at the output, whether it be the actual velocity or the isentropic velocity. And if the inlet velocity is small, we can assume that it's 0. So H1 is equal to H2 actual plus V2 actual squared over 2. And then our nozzle isentropic efficiency is just this. That example is in your book, so I'll skip it because class is done.